start the recording. So again, we are starting with the labs on Monday. So again, please make sure that you know your lab sections and you know your TAs. The lab notes are already uploaded and TAs are probably helping you over the GroupMe chat. So please join the GroupMe chat as well if you haven't joined already. And also please look at this video that was posted by one of the TAs in a previous year on how to solve the problems for lab 1. Okay. And let me know if there are any questions. Also, please post in GroupMe. Yes. So over here. So for all the lab notes will be here. So let's say, for example, the lab problems are here, lab 1 input and output resistances. If there are some reference materials that are provided as well, notes on how to find resistances, measurement errors, there's documentation on the dashboard. Also, there's this video from last year's TA Office Hour 1, where the TA actually showed how to solve the problems in lab 1. Okay, so please go through the Canvas page and you'll find all the material over there. All right. Okay, so in the last lecture, we looked at something interesting that, okay, we all of us know how to solve problems, op-amp related problems when the op-amp is ideal, but we also saw scenarios when the op-amp is non-ideal and how to find out the overall gain of the system in that case. And the approach that we are going to follow is, again, I'll just repeat it, that you need to find out two quantities. One will be called A infinity. The other one will be called T or loop gain. Now, A infinity is the gain of the system if the op-amp had been ideal. If the op-amp had an infinite gain or infinite input impedance, that's what we'll have for A infinity. So this is, the numerator is exactly same as what you learned in 3111. The denominator contains the non-idealities. So when you're calculating the loop gain, of course, you'll be considering that the op-amp does not have infinite gain. You'll consider the op-amp does not have an infinite input impedance, and the op-amp would also have a non-zero output impedance. So all of that will be part of this T or loop gain. And as you already saw in the previous lecture, that there will be two parts of the loop gain. One, of course, the gain of the feed-forward path. That's the gain of the op-amp itself. So the gain of the op-amp itself is A, but then you would like to find out what amount of this voltage, the voltage that is available at the output of the dependent voltage source, what percentage or what fraction of this voltage is available back at the input side. And when you say input, you need to remember that the input is between the positive and the negative terminal of the op-amp. So between the positive and the negative. We are not talking about the input, which is was the original input voltage source. So what fraction of the output voltage over here is fed back at the input side between the positive and negative terminals of the op-amp, that is the top and bottom terminal of your input resistance Ri. And in the last lecture, we found out that how to use these voltage divisions. So as you see that there are 3 different voltage divisions in the beta factor or the feedback factor. And of course, this Rx and Ry, these were resistors that we used for simplification. So Ry, for example, is the resistance that you see looking down at this particular node, and Rx is the resistance that you see looking on the left side at this particular node. So of course, you can also write down what is Rx and Ry in terms of your known resistances, R1, R2, R3, and so on. And then you can find out what would be your beta. Then you find out what is your T by multiplying A with beta. And when you know T, now you can go back to this original equation on the previous page. The non-ideal op-amp's overall gain is A infinity divided by 1 plus 1 over T. And we already showed how to derive this particular formula, right? So A infinity will be the ideal op-amp's, the gain of the system with the ideal op-amp. And then you already found out T, so you know what would be the gain of the system with a non-ideal op-amp. All right. Now, a few other things that we'll learn, which will be important for your homework number 2 as well. So just a note that homework 2 has been posted. And then, for example, you see, so this will be due next Friday, September 19th. Now, for each of these circuits below, first you need to find out A infinity. So that's going to be pretty easy because you assume the op-amp is ideal. And with ideal op-amp assumption, you just find out what is the gain of the system. Okay. So op-amp's gain is infinite, but A infinity means the gain of the system when the op-amp's gain is infinite and when the op-amp's input resistance is infinite and so on. The other things that you need to find out is Rin, the input resistance as seen at this particular terminal, for example, or this particular port. Also Rout looking at this particular port over here. And we'll see some examples today how to find out Rin and Rout. And then finally, part D is the loop gain for each circuit. And when you talk about loop gain, that's basically T or A times beta. So you know what would be the gain of the op-amp. So the gain of the op-amp is given to be 500. So part D is the scenario where we are talking about non-ideal op-amps. Part A, B, and C, these are all for ideal op-amps. Right? So for Rin, you can assume that the op-amp is ideal. Rout, just assume the op-amp is ideal. A infinity, assume the op-amp is ideal. For part D, we have the non-ideal op-amp, where you are provided the value of non-infinite or a finite gain of the op-amp, which is 500. See, this is not infinite anymore. The input resistance, again, not infinite anymore. It's just 100 kilo ohms. And the output resistance, again, not 0 anymore. It's 1 kilo. So there you need to find out the beta factor, just like we did in the previous class. And then multiplying beta with A, you get the loop gain. So that will be your part D. Again, there are multiple questions like this, I think 3 questions. There is an ungraded part which we haven't talked about yet, but in Monday's lecture, we'll talk about the frequency response of the closed loop scenarios for ideal and non-ideal op-amps. So this part will be ungraded, so don't worry about this. But if you just want a practice problem, also you can go through it. But we'll discuss about the frequency response of the op-amps in the next lecture. Okay, so it's clear about the homework 2 and what we need to do, right? All right, so deadline is next Friday. Now let's get back to how to find out Rin and Rout. So we are going back to the same document that is already posted on Canvas. Now there are a few definitions. Again, some of these you already know, but I'd just like to repeat a few things. For example, the terminal is a node in the circuit that is made available for connection to other parts of the circuit. So basically any node in the circuit is going to be called a terminal. Now, what is a port? You'll hear about this term port a lot in RF circuits specifically, because in RF, some of you already know that it's all about 50 ohm input and output resistances, because you need to do input and output matching in RF. We'll not talk about matching in this course, but the port impedance, which needs to be 50 ohm for RF, is again a very important concept over there. Here, we are just defining what is a port, and the port is a pair of terminals. This is basically 2 terminals in which the current entering one terminal will be equal to the current leaving the other terminal. So you define the port in a way so that it's basically a pair of terminals in your circuit. The current entering one of those terminals is same as the current leaving the other terminal. Okay, so that's how a port is defined. When a port is terminated, that means that you have connected something at that port. It could be a load resistance, it could be a load capacitance, it could be some other circuit, and you're terminating the port with something else. When the port is unterminated, that means you have nothing. You basically have an open circuit for that port. So remember your Thevenin equivalent when you're trying to find out the Thevenin equivalent resistance for a black box. So what you're trying to do is basically look at this port and find out how much resistance do you see looking into the black box from the output side. Okay. Why do we call this a port? Again, from the definition, if you put a voltage source over here, let's say you put a voltage source, test voltage source over here, the current entering the black box will be same as the current leaving the black box and coming back to the source, right? So again, it satisfies the definition of the port. So that's how you can remember that what is a port. Just remember this example of how we find out Thevenin equivalent resistances or voltages. And what we basically do is find out the Thevenin equivalent resistance at the output port or the input port and so on. Now, if you have nothing at the output, so for example, initially, let's say, just remove the connections over here. So initially, let's say you had a resistance over here, right? This is, let's say, RL. And what that says is basically this port, the set of these 2 terminals, that is terminated with a resistance RL. But if you had nothing, if you had open circuit, which you anyway do when you start calculating the Thevenin equivalent resistances, then you unterminate the port. Make sure that the port has nothing and you have open circuit. So again, just some definitions, but I just wanted to sort of connect those definitions with what you already know. All right, you can go through the rest of the text. There's not a lot of important things here, but let's look at some of the examples that will help you understand the concepts. So when you, and some of these concepts you already know. For example, you already know how to find out the Thevenin equivalent resistance in a black box, right? So first you kill all the independent sources, that is you open circuit all the independent current sources and you short circuit all the independent voltage sources. That's the first thing you need to do, because eventually you are going to put a test voltage source and or a test current source to find out the resistances, and you don't want the voltage or current sources to fight with each other. That's the whole idea why you kill all the independent sources in the first step. That you don't want multiple voltage sources, independent voltage sources in the circuit, they will fight with each other. Okay, so how do we find out output resistance for a circuit? Again, the output resistance is nothing but the Thevenin equivalent resistance at the output port. So this is the output port for the black box. What you do is that you either connect a test voltage source, let's say Vx, and find out how much current is going in. Of course, because this is a port, the same amount of current will come out of the black box as well. The ratio of Vx to Ix will give you the output resistance at the port. Similarly, if you had connected a current source Ix and found what is the voltage that gets developed at the output node, let's call that Vx, and then the ratio of Vx over Ix will give you output resistance Rout. Now, in both of these methods, you'll see you'll end up with the exact same Rout. So again, whatever method you apply, Thevenin equivalence, Norton equivalence, everything will boil down to the same final number for the Rout. Okay, now if you want to find out the input resistance, let's say you want to find out the Rin. So what do you do in that case? You do this, you have the same approach, exact same approach. So to find out Rin, you either connect a current source or a voltage source, a test voltage source or a test current source at the input side. If you're connecting a test voltage source, you find out how much current is going in the circuit. If you're connecting a test current source, then you find out how much voltage is developed at the input of the circuit. And the ratio of Vx over Ix is going to give you your Rin. So again, finding out the Thevenin equivalent resistance at the input port. That's what is meant by an input resistance. All right. Now, one thing that is interesting is if you connect an RL, let's say you have this black box, and at the output of the black box, let's say you connect a load resistance. Now, if you're looking at the input resistance, that is the input at this terminal, right? Input of the black box at this terminal, if you're looking into the input resistance. One interesting thing that you see, that looking on the right-hand side, you do see RL. You'll see the black box. You'll also see RL. Now, if it is completely isolated, if there is an isolation element within the black box that completely isolates RL from the input side, of course, you'll see no effect of RL. But assuming that, okay, the black box is a, let's say, combination of resistances, maybe something like this, right? So in that case, whatever you connect on this side, whatever you connect as the value of your RL, that will determine, that will impact the effective resistance that you see from the source side. So unless there is an isolating element, let's say you put something within the black box that isolates your load from the input side, in that case, the load will have no impact. But in general, the circuits we'll look at in this course, you'll see that changing RL will have an impact on the input resistance. However, if you change RS, that will not have any impact on the input resistance if and only if you're looking at the input resistance from this point onward. So you're defining your input resistance at the right-hand side of RS. So whatever you connect as RS does not matter, right? So if you're looking at on the right-hand side of this particular terminal, it does not matter what is connected to the left. So on the input impedance, RS does not have any impact, but RL can have impact. Similarly, on the output impedance, if you're looking at the output from the output side toward left, if you have a source resistance RS, for example, the same source resistance of the voltage source, and if the value of that source resistance changes, that will have impact on your Rout. But the load resistance does not have any impact on your Rout, because again, remember Thevenin, that you disconnect your RL, you remove your load resistance, and then you start measuring your Thevenin equivalent resistance, right? Because looking at this terminal, if you're trying to look to the left side, whatever is connected to the right does not matter. Because you're only interested in what you see on the left side of this output terminal. not on the right side. So bottom line, your input source resistance can have an impact on your output resistance, and your output load resistance can have an impact on your input resistance, but not vice versa. Right? So input source resistance does not have any impact on the input resistance, and output load resistance does not have any impact on the overall output resistance. All right. So with that in mind, let's maybe we can take a look at a few examples. Okay. So some of these examples are very similar, very easy to understand, and you have looked at some of these circuits in your 3111. So for example, this particular circuit over here, if you connect, let's say, a voltage source at this point, right? So this is your inverting amplifier, right? That you have a R1 resistance connected to the inverting terminal of the op-amp. You have a feedback going on from the output terminal to the inverting terminal of the op-amp. And the non-inverting terminal is connected to an AC ground. Again, I'll re-emphasize the fact that this is an AC ground, which means that this could have been a DC voltage. But for AC analysis, whenever you're thinking about gain, so whenever you're thinking about gain, you're always calculating in terms of AC, because there's no meaning of DC gain for an amplifier. It's always AC gain. So if you see a ground in an amplifier circuit, it's an AC ground, which means it can have a DC voltage though, right? And that DC voltage is basically the bias voltage. Remember that we talked about these voltage transfer characteristics, or VTC. If this is your V in and if this is your V out for the amplifier, what is the gain? The gain is basically the slope of this curve, dVt over dV in, dV out over dV in, or basically the derivative of V out with respect to V in, or the slope of this curve is the gain, correct? So you want to be at a point where your gain is maximum. Your gain is 0 over here. Your gain is almost 0 over here. So where do you want to be? You want to be somewhere over here. That means first you have to start at a DC point, which is almost at the middle of your voltage transfer characteristic. That means almost at the middle of, at the midpoint between your VDD and VSS. So if your VDD is 5 volt and VSS is 0 volts, it's a good idea to have all the DC potentials set at, let's say, 2.5 volts. Right? Then only you can expect gain, because then you are in the middle of this voltage transfer characteristic. And then if you have a small perturbation in the input voltage, if your gain is more than 1, you'll have a large perturbation in the output voltage. Also, if you think that if your VDD is, let's say, plus 5 volt and VSS is minus 5 volt, you might get away without applying a separate bias. Why? Because if your VDD is plus 5 and VSS is minus 5, so the maximum voltage that this voltage transfer characteristic has is plus 5 volt, and the minimum voltage is minus 5 volt. What is the midpoint of plus 5 and minus 5? It's 0 DC, right? So even without applying a, let's say, non-zero bias voltage in your circuit, you can get away with it if you have a 5 volt VDD and minus 5 volt VSS. In some of the labs, you'll see it, that if you have a positive VDD and negative VSS, you may not need a bias because your bias point is near 0 anyway. But if your VDD is plus 5, VSS is 0, then you definitely need to apply a bias, which should be around 2.5 volts. Okay, now getting back to R in and R out. So this was your very simple inverting amplifier configuration. It's just that we have gotten rid of the independent voltage source which was connected at the input. So for your inverting op-amp configuration, this is where your input should be connected. But we got rid of it because you just want to find out the Thevenin equivalent resistances. So you get rid of all the independent voltage and current sources. Okay, so if you want to find out the Rin at this terminal, for example, right? What are you trying to find out? You're trying to find out if I put a voltage source at this point. So let's get rid of the other voltage source first, because we don't want the circuit to get confused with multiple voltage sources. So let's say I connect one test voltage source over here. Let's say Vx. Okay. So what I'm trying to find out is how much current goes in, or how much current goes out of Vx and goes into the op-amp's positive terminal. So how much is that current? What is the input resistance of the ideal op-amp? Infinitely large, right? So that means no current can go in the op-amp. If current cannot go in the op amp, that means there is no current going out of Vx as well, because Vx is only connected at that. So if Ix is 0, so my Ix, let me write that down, Ix is equal to 0, and Vx is some finite value, of course. So what would be Vx over Ix? Infinitely large, right? So that's why your Rin is infinite in this case. Okay. What is going to be your R out? Again, assume that this is an ideal op amp. No need to complicate things right now. Let's just assume that you have an ideal op amp. What is going to be the R out in this case? Of course, for the ideal op amp, if you look into the op amp's this terminal, the resistance is 0, right? Because remember what does the model of the ideal op amp look like? It looks like just this dependent, if this voltage is, let's say, VD, differential input voltage, then you have a dependent voltage source over here, which is A times VD. Now, if this is an ideal op amp, then the output resistance of this dependent voltage source is going to be 0. So if there is a resistance over here, the value of this resistance is going to be 0, right? So if you look into an ideal op amp's output port, what is the resistance that you're going to see? You're going to see 0 resistance, right? Because this resistance is 0, so it is as good as a short. And then you see this voltage source, which anyway has 0 resistance, right? Voltage sources have ideally 0 resistance. So looking into the ideal op amp's output port, you see 0 resistance. But looking into the output port of this circuit, that may or may not be 0. In this case, this is just an example. But keep in mind that in all scenarios, Rin may not be infinite for the system. For the op amp, the Rin is infinite. If you just consider this op amp, this part, the Rin is always infinite. The R out is always 0. There's no question about it if this is an ideal op amp. But even if this is an ideal op amp, for the full system, for the full circuit that you see with all these resistances connected, the input resistance may not be infinite, the output resistance may not be 0. Although in this particular case, it is infinite and 0 because of the way we are looking at the input and output. You're saying that, oh, my input terminal is this one, my output terminal is this one. So we already saw why Rin is infinite. Now, why R out is 0? Let's just draw this circuit once again on the output side. So you have this input side, which is open because I'm assuming this is an ideal op amp. The output resistance is 0. Then you have this R2 resistance connected back at the input side. So you have this R2 resistance connected back at the input side. Now at the input side, because your positive terminal is connected to AC ground, so this point is AC ground, what that means is that because this is a negative feedback, you're connecting back your output to the negative terminal of the op amp. So this is a negative feedback. Because this is a negative feedback, you will have the virtual ground property, which means that this terminal is also connected to ground, AC ground effectively. And this point is also ground because this is the reference terminal of the output voltage source, the dependent voltage source. Now what we are saying is that we are looking into this terminal or this port between the output terminal and the ground terminal, let's say. So you're looking into that when you draw this circuit. So how much resistance do you see looking on the left side at this port? Of course, you see two parallel paths. Let me draw it with a different color. You'll see two parallel paths. One path of the current can go through this and can go to ground. The other path is through this, right? There are two parallel paths. One of them goes inside the op amp and goes to the ground that is inside the op amp. The other one goes around the op amp and then again connects to an AC ground because of the virtual ground property of the op amp. So you have two parallel paths. One of the parallel paths have 0 resistance. The other one has R2 resistance. So you have a parallel combination of 0 and R2, right? This path has 0 resistance and this other path has a resistance of R2. And both of them are going to ground, right? So that's why they are parallel paths. So what is a parallel combination of 0 and R2? It's 0. So your R out is going to be 0 in this case. However, if this had been, let's say, R3, let's say there is a R3 resistance connected at the output terminal of this dependent voltage source. Then what would have been the output resistance? That would have been R3 in parallel with R2. Even though you do not see R3, R3 is hidden inside the op-amp. R3 is the output resistance of the op-amp. So if the output resistance is non-zero, that is the non-ideal scenario of the op-amp, right? So if that were R3, the output resistance looking here would have been R3 in parallel with R2. Question?
For an ideal op-amp, does there exist a port where one of them has like direct, like a wire straight to the op-amp's output where the receiving piece is not zero?
For the ideal op-amp, if you have a wire directly connected to the op-amp's output, and if you're looking at that particular terminal, of course, it will always be zero, because you'll always have a zero resistance in parallel with a non-zero resistance, right?
The other end of the port.
Yeah, so you're looking at this port. So basically, drawing like this, that means that you're looking at this terminal and between the ground, because here, basically, let's say you have the ground. So between these two terminals, which is the other end, which is ground, and the other side is basically the terminal that you are looking at, right? So for an ideal op-amp, it will always be, Rout will always be zero if you are looking at a terminal which is the output of the op-amp. Okay. So let's take a look at a few other examples. Now, in this case, again, what we are doing is that instead of looking into this terminal, which we did earlier for the previous scenario, see, we are looking at this terminal, the positive input of the op-amp. Here, let's say you just look into the negative terminal of the op-amp, the inverting terminal of the op-amp. And now we're saying that Rin is equal to R1. It's not infinity anymore. Why? Because again, think about this, that your non-inverting terminal is an AC ground. This is a negative feedback circuit, which means due to the virtual ground property, the negative or the inverting terminal will also be virtual ground or AC ground, right? So what are we looking at here? If you connect a test voltage source Vx at this point, you will see this resistance R1 connected to a AC virtual ground. Because of the virtual ground property, you have a ground over here. So looking at the, looking on the top side from Vx, what you're going to see R1 being connected to a ground. So basically the circuit looks like this. You have a Vx, you have a resistance R1, and then that resistance goes back to ground. So how much resistance do you see here? You see R1, right? So you do not see an infinite, okay, now here's the fun part. At this point, you are also connecting the ideal op-amp's negative terminal, right? If you look here, the ideal op-amp's negative terminal is connected at this point. But what is the parallel combination of, which is basically infinite resistance? Looking here, you have an infinitely large resistance. But at this point, here you see a zero resistance to ground. What is the parallel combination of zero and infinity? It will still be zero. Like current will always take the least resistance path, which is this one. What is more interesting is that you also had this R2 resistance connected to the same terminal. So you actually had R2 connected here, connected back to the output of the op-amp, which means that it is getting connected to a ground. So there is the resistance R2 as well. But current does not go to this path. Current does not go to this path. Why? Because it already sees an AC ground here. The current can go to the AC ground directly. Current does not need to take the path of more resistance. It will always take the path of least resistance. And in this case, the path of least resistance at this terminal is zero, because that is directly connected to the AC ground. And that is the reason why you have a combination of basically this R1 connected to this node, which is connected with a zero resistance to ground. And that is in parallel with the infinite resistance of the op-amp and the R2 resistance connected in the feedback circuit. But zero in parallel with anything is zero. And that's the reason why all of this does not matter. The only thing that you see is the R1 resistance. Okay. All right. Now let's take a look at one more fun example. What is happening here? You are trying to look at the resistance looking into this port. Again, you see two terminals. So you're basically intersecting these lines, which means that you're looking into this port where one terminal is this one, the other terminal is this one, right? And you're trying to find out how much resistance you are seeing. And you already see that there is a resistance connected between the two terminals, which is R1. But still, I write that R in is equal to 0. Why is that? Again, say this is an op-amp connected in the negative feedback configuration because your output is going back to the negative or the inverting terminal, which means virtual ground property does hold. What is the non-inverting terminal of the op-amp connected to? It's connected to an AC ground. Since virtual ground property is applicable, the negative or the inverting terminal is also connected to AC ground effectively, right? So if you connect a voltage source at that terminal where you're trying to find out R in, let's connect a voltage source Vx over there. What you really have is this resistance R1, but the top terminal of the resistance R1 is connected to AC ground, right? Because of the virtual ground property. The bottom terminal of the resistance R1 is also connected to AC ground. See, the bottom terminal of the resistance is also connected to AC ground. So basically you have a short between the top terminal and the bottom terminal of the R1 resistance, which is an AC ground. What is 0 in parallel with R1? 0. So your Rin in this case is equal to 0. So be careful about how the circuit configuration looks like, but this will lead to, your homework 3, homework 2, the 3 problems that you have to deal with is basically trying to find out what is the Rin and Rout at respective terminals, right? So just go through that. Let's look at a few more examples in today's class, but be careful at which terminal you're trying to find out Rin or Rout. Yes. Yes. Yes, and why is that? Because you have a negative feedback. What is the job of the negative feedback is to make the circuit stable, that you want to have a 0 difference between the two inputs. Think about the thermal regulation scenario that we talked about in the class, that you want 37 degrees centigrade on your body, right? If it rises, you want to bring it back through a negative feedback to 37 degree so that the difference between the target and the original temperature is 0, right? Here, the difference between the target and the original, which is basically the positive and the negative feedback, negative terminals, you want to make that 0. That's the whole idea of the negative feedback, right? And that is the reason why virtual ground property exists. That you want to have 0 difference between the inverting and non-inverting terminals of the op-amp because you have a negative feedback. If you have a op-amp in open loop, you cannot expect a virtual ground property. Let's say you just have an op-amp, right? You buy a op-amp from market. You have, let's say, positive and negative. Let's say you connect one of the terminals to ground. This will not mean that the other terminal is grounded. This is not virtual ground property. Virtual ground property will only hold true if you are trying to stabilize the voltages in the system through a negative feedback. Until and unless you have the negative feedback, there's no virtual ground. Yes. What do you mean by any resistive network? Right. On the negative feedback. Yeah, you can have resistive, capacitive, inductive, any kind of negative, or you can have more op-amps. Like it is a possibility that you have another op-amp in the feedback path. You can do that. Like we'll look at some of those examples later as well. But the important idea is that you're feeding back some part of the voltage from the output side back to the negative input over here, so that you're subtracting the output from or subtracting the feedback signal from the input signal, and you want to have a 0 error over there. And because you want to have a 0 error, 0 is ground, right? That's the meaning of virtual ground. Yeah, that's a voltage follower. Okay. So that's also negative feedback. Voltage follower is a negative feedback. Okay, but if you have an open loop op-amp, let's say you buy this op-amp from market and then just connect the positive terminal to ground, you will never see your negative terminal being connected to ground, AC ground. Right? It's just not possible because that's not how virtual ground works. Okay, so look at some of these examples. So for example, let's say for a non-inverting amplifier, I'll probably not go through all the examples, but please do it at your own pace. I have given multiple examples over here where you can find out what is the A infinity, R in and R out. That will help you solve the homework 2 problems. So for example, if you have this non-inverting amplifier, you know A infinity, which is the gain of the system, assuming ideal op-amp conditions, that is going to be 1 plus R2 over R1. Again, I'm not going to solve it. I'm assuming you can solve it yourself through nodal analysis or through the use of KCL, KVL, in whatever way you like. Rin, if Rin is being looked at this terminal, which is basically the positive terminal of the op-amp, of course, you have no current going in, so Rin is infinite. R out, looking at the output terminal, so whatever you connect in parallel, inside of the op-amp, there is a direct path connecting to ground because you had this dependent voltage source, and the dependent voltage source's output resistance is 0 if this is an ideal op-amp. So inside, looking into the op-amp, you have a direct path connected to ground, and you're connecting other things in parallel, so that does not matter. So this does not matter, this does not matter, and so on. So your R out is going to be 0. Okay? All right. Next, voltage follower, the example that you are asking. So what does voltage follower mean? That without connecting any resistor, so you basically have this same configuration that we had. Okay, let me go back a little bit. So it's basically the same configuration that you have here. What is the only difference? The difference is that your R2 is 0 and R1 is infinitely large, right? We are not connecting any R1 to ground. So if you make R1 tending towards infinity in the above circuit, and if you make R2 tending towards 0, 1 plus R2 over R1 will become 1. So A infinity will become 1. So the gain of this system, if R1 is infinitely large and R2 is 0, then A infinity will be equal to 1, right? Just from this formula, 1 plus R2 over R1. That's 1 plus 0 over infinity. So, and it will be the same if R2 is not 0 as well. Like, let's say, just make R1 equal to infinity, a finite value divided by infinite will be 0. So, for this case, for the voltage follower, your R2 is 0. That's why you have a direct short from the output to the negative terminal of the op-amp. And your R1 is infinitely large, so you just don't have it. You have an open circuit. So your A infinity is equal to 1, which means you have a gain of 1, right? If your input looks like a sine wave, like this, your output will exactly look like the same sine wave. Now you may ask, what is the need for the voltage follower then? If I am not getting any gain, why do I even have this circuit? The answer is that sometimes you are not only looking for gain, you are also looking for driving capabilities, right? You may have a circuit and you have a load, but let's say, what does load mean? Load means that you need to draw a certain amount of current, right? Load means you have to draw a certain amount of current. But does your source capable enough to provide that much amount of current to the load? The answer might be yes or no, depending on how you have configured your source. For an ideal voltage source, yes, it will always drive any load. But for a non-ideal voltage source, or maybe, and you can model a part of your circuit as a non-ideal voltage source, you may see it's not capable of driving a load, a particular amount of load. The voltage follower is used so when the source does not have enough driving capability to drive a large load. And if you assume that this is an ideal op-amp, that means you have an ideal dependent voltage source here. And that ideal dependent voltage source, right? That ideal dependent voltage source can drive any amount of load that is connected to your output. That is the reason why you'll be using a voltage follower, because that is useful in the scenario when this VS, this voltage source at your input, had, let's say, a very large, let's say, a 1 mega ohm resistance connected to it. Right? Let's say there is a 1 mega ohm resistance. So this is a very much non-ideal voltage source at the input. However, if your op-amp is ideal or close to ideal, let's say op-amp has a output resistance of 50 ohms. 50 ohms is much better than 1 mega ohm to have. So that's why the voltage follower helps you to get the same voltage at your input. So whatever voltage this voltage source was providing, even though this was a bad voltage source, you'll see the same amount of voltage at the output, but with better driving capability. That's the reason why you'd sometimes want to use a voltage follower, and we'll look into more details of this like after our midterm exams and so on, right? So what is there inside the voltage follower? That's what we're going to look at. All right. So again, you can find out what is your R in and R out. In this case also, you'll see R in is 0, R in is infinite, R out is 0, and so on. All right. So for the inverting amplifier, where you have the input voltage source here, you have a resistance R1, you have R2. And remember that this is basically a negative feedback once again. So if you have a virtual ground here, you'll also have a virtual ground on the inverting terminal as well. So in that case, your R in will be equal to R1. Because at the right-hand side of your R1 resistance, you see a virtual ground. And that's the reason why if you connect a test voltage source over here, there will be a current flow through R1, and that current will terminate at that virtual ground. So R1 is not, R in is not infinite. R out, although in this case will be infinite, as we saw in the previous scenarios. So you can look at similarly other examples such as summing amplifiers, current to voltage converter. So maybe let's take a look at this one, a current to voltage converter. How does this work? Right? And the way a current to voltage converter we have represented it is that let's say you have a current source at the input side, and that is being connected directly to the inverting terminal of the op-amp. The non-inverting terminal is connected to the AC ground, and you have this feedback, basically this negative feedback from the output to the inverting terminal of the op-amp. So what is happening in this case, that whatever current is flowing in, right? You have, if you want to find out the R in and R out as well as A infinity. So when you're trying to find out A infinity, it's basically whatever current that is flowing in, and eventually what is the voltage that you see at the output side, what is the ratio between this voltage and the current, right? So your output is a voltage, your input is a current. The gain is voltage over current, so that is an impedance. So this is going to be called a trans-impedance amplifier. Your transfer function is an impedance because your output is a voltage, input is a current. Again, assuming ideal op-amp considerations, you can find out what is your A infinity, and A infinity is going to be minus of R2. You'll see that your A infinity is going to be minus of R2 in this case. What is going to be your R in and R out? Again, if you connect a test voltage source over here and assume the virtual ground properties, then your R in and R out both are going to be 0. All right. Now, if you had the opposite of this, let's say a transconductance amplifier. For a transconductance amplifier, you are providing an input voltage source, let's say at the non-inverting terminal, and then you are interested in the current that is flowing from the output, right? So IO is your output and VS is your input. So you're interested in IO over VS, right? That is your A infinity. That's the gain, transconductance gain, when you have an ideal op-amp. And again, you can find out what would be the value of that transconductance gain. That is going to be 1 over R1. All right, so again, why is that? Just think about it. So this point's voltage is VS. So this is VS. You have a virtual ground property in this case. Why? Because you have this negative feedback. So your virtual ground property will hold. Now, virtual ground property does not mean you have a ground. Again, that's another important concept. Virtual ground property means is that the effective difference of voltages between the positive and the negative terminal of the op-amp, the effective difference of the voltages is same as ground, that is 0. So if you have a voltage of Vs connected at the non-inverting terminal of the op-amp, you have the same voltage Vs. So this point's voltage will also be Vs at the inverting terminal of the op-amp. That's what virtual ground property means, that the voltages will be equal and the differences will be equal to the ground voltage, which is 0. Okay, so if this point's voltage is Vs, okay, so this point's voltage is Vs, this is the current that you're interested in. No current can go into the op-amp because this is an ideal op-amp. So whatever current is flowing IO through this ZL, through this load resistance ZL, whatever current is flowing here, the same current will flow back through the, or flow through the R1 resistance to ground. Right? This is the path of the current flow. no current can go inside the op amp. If this is the path of the current flow, your IO is basically equal to the current that is flowing through through this R1 resistance. The output current is same as the current that is flowing through the R1 resistance because there is no current division here. Let me clear this up once again. So this is the current that is flowing. So IO is same as the current that is flowing through R1. What is the voltage across R1? The top terminal of R1 is equal to Vs due to the virtual ground property. So Vs over R1 is equal to IO. So if you want to find out IO over Vs, which is the transconductance gain, output over input, IO over Vs, that is going to be 1 over R1. So this is your transconductance gain. And just look at the units again. 1 over R1. So 1 over resistance. 1 over resistance is a conductance. Right? And this also says that you have a transconductance as your transfer function. Because you have 1 over resistance, that is conductance. What is the input and output resistances in this case? Input resistance Rin, right? Input resistance is Rin over here. Again, no current can go in this terminal, right? Because no current can go in, your Rin is equal to infinitely large. What about Rout? What about the output resistance in this case? And that's where it is going to be interesting. All right. So now if you look at this particular scenario, that I want to find out what is my output resistance in this case. So I'm looking at my output terminal. But remember, when you try to look at the output terminal, okay, so this will require a little bit of, so for example, next day, maybe I'll start with this, that why your Rout is going to be infinitely large, right? Because I need to draw the circuit, and I think that today it's already 11:30. So let's start with this in the next lecture. And in the next lecture, I'll also start with the frequency response of the op amp. If you look at your Canvas page, there are certain examples provided. So look at these op amp example and self-study the more loop gain examples. So just go through some of these examples. It will follow the same concepts that we just studied in the last 2 lectures. So go through these loop gain examples. It will make your concepts much clearer. In the next lecture, I'll look at that Rout first, and then we'll start with frequency response of non-ideal op amps.